Good morning, good afternoon, good evening, class. This is Mr. Arocena, and on today's video, we're going to talk about strong and weak acids and bases. Because I think I briefly mentioned in the last video that strong acids and weak bases are different, and we didn't quite explain why. So we're going to go over that today. Right. So one thing we have to define, I suppose, is what actually is a strong acid versus a strong base, strong acid versus a weak acid, and a strong base versus a weak base. And it's not quite what you would think. I think I mentioned in the last video that you shouldn't confuse, I suppose, strong acids with dangerous acids, because the strength of an acid is actually not what defines how dangerous it is. As far as our definition of strong acid or strong base goes, it goes into what's known as dissociation. So basically, dissociation is how ionized the acid or base is. Basically, how many ions can this base or can this acid create. A strong acid will 100% ionize, or in other words, it'll 100% dissolve when put into solution. So all of it gets turned into its separate ions, or it'll release as many ions as it can release. So an example of a strong acid, or a strong base and strong acid, is as follows. So this is sodium hydroxide. Sodium hydroxide, if you remember from your solubility, alkali metals are generally always soluble. So sodium hydroxide will fully dissolve into sodium ions and hydroxide ions. Okay. Similarly, another strong acid or strong substance is hydrochloric acid. Here, hydrochloric acid will fully dissolve into hydrogen ions and chloride ions. So a strong acid is something that fully dissolves, so 100% ionized or dissolves fully. Okay. Now, by contrast, a weak acid is a substance or a weak base. These are substances that don't dissociate 100%, or they don't fully dissolve. These ones are more interesting because what happens is that in the act of dissolving, they reach a point where they reach an equilibrium point. So basically, they dissolve enough that then the reverse reaction equals as much as the forward dissolving reaction. So these are two examples of a weak base in ammonia. So this is ammonia. Notice that our reaction arrow is now double-sided. So this sets up an equilibrium. So an equilibrium is set up. I think I mentioned acid-base equilibriums in the last video. Weak acids and weak bases will always set up an equilibrium because they don't fully dissociate. This is hydrofluoric acid, and again, notice it will create an equilibrium with its ion form. Okay, so that's the difference between a strong acid and a weak acid, and a strong base and a weak base. So strong acids and bases will fully dissolve, and weak acids and bases do not. Oops, bases do not. Okay. And that's really the difference between a strong acid and a weak acid, and a strong base and a weak base. Strong acids and strong bases aren't necessarily more dangerous than weak acids or weak bases. What makes an acid dangerous to the end user is really how concentrated they are. And we'll talk about that in a moment. So acid-base equilibriums, like I mentioned in our last video, they always involve weak acids and bases because they do not fully dissociate, and they will create equilibriums. Okay. Now, as I mentioned, we don't want to confuse weak and strong with dilute and concentrated. So weak acids don't necessarily mean dilute acids, and strong acids don't necessarily mean concentrated acids. And this is where the danger of the acid comes in. So this will determines kind of like the danger of the acid or base. Okay, so how dilute or concentrated they are determines kind of just how dangerous they are. But there are some exceptions to that rule. So here's an example. Let's see. This is a 10 molar hydrofluoric acid is a very concentrated weak acid. And by contrast, a 0.001 molar hydrochloric acid is very dilute, but is still considered strong. This substance here, the high concentration of hydrofluoric acid, will be more dangerous in general because the huge concentration of acid allows it to force the equilibrium to go forward. So if I think about my equilibrium, HF, this is aqueous plus water moving in this equilibrium to create hydronium and fluoride ions. If I have a very large concentration of this, my equilibrium will tend to shift forward. So this is what causes the forward reaction to, I guess, continue moving forward because I have a large concentration of hydrofluoric acid. By contrast, this reaction here, this is a strong acid already, so if I combine this with water, this will go in one way to H3O plus and Cl minus, but because the concentration is so low, the amount of actual hydronium, this is the thing that makes an acid, this is actually quite small, very small, because of low concentration. So this particular acid, if you split on yourself, won't actually do much to you because it's very, very dilute. Whereas if this acid you spill on yourself, that could actually do quite a lot of harm because it's very, very concentrated. Okay. In this regard, this is why we always, in the lab, we always tend to use very, very small concentrations. Generally speaking, most lab manuals will tell you to create acid concentrations of 0.1, and I think some junior science labs will have it at 0.01. These are very, very safe concentrations. If you spill them on yourself, it generally won't do much to you as long as you wash it off right away. But at the same time, because there's not a lot of actual acid concentration, when we do acid-base reactions, this substance here, you don't get a lot of it, so the reaction itself tends to be pretty mundane. So I always end up making my concentrations larger so that we can create more of a reaction. But as I always warn you guys that it's sometimes a little more dangerous because of the higher concentrations. Concentration is what determines how dangerous the acid is in general. Okay. There are some exceptions to that. Like I think hydrofluoric acid, no matter what concentration it in, is quite dangerous. But that's again one of the exceptions. All right, now the strong acids, there are generally 6 strong acids we deal with, and you can tell where they are if you look at the table of acid and base strengths. So I'll just pull that up quickly for you. So in your Chem data booklet, you have this table, the relative strengths of Bronsted-Lowry acids and bases. These 6 here, the top 6 here, so these 6 here, these are your strong acids. So your strong acids are. All right, so here is the table. So these are our strong acids. So these 6 acids will always fully dissolve. Okay, and they're all, except for sulfuric acid, they're all monoprotic. So perchloric acid, hydroiodic acid, hydrobromic acids, hydrochloric acid. These 3 are halogen acids. The only one that's hydrofluoric acid is actually not a strong acid despite being a halogen acid. Nitric acid, very good for dissolving precious metals like gold and silver. And then sulfuric acid. So these are all strong acids. Now, one thing I will make mention here, sulfuric acid is really interesting because it is diprotic. You would think that because it's a strong acid that it dissolves into 2 hydrogen ions. It actually does not. Sulfuric acid will actually break down into 1 hydrogen and then this one here. This is, I think, sulfurous. No, H2SO4 is It's actually a weak acid. Oh, there it is, hydrogen sulfate. Yeah, the hydrogen sulfate ions down here. But anyways, yeah, so the sulfuric acid, the strong acid is actually the sulfuric acid, but it only gives up one hydrogen, and it becomes HSO4 minus. And HSO4 minus is down here, which is not a strong acid. So it's really interesting. But anyways, says these are your strong acids. Strong acids are these substances. Whoops. Are these substances here. Okay. All right, now everything else on the table ends up being a weak acid. Okay. Oh, then the other thing you want to notice, I'll go back here for a moment, is that all of the reactions are one way. So they will go forward, always forward. Okay. So if you have a sample of hydrogen iodide in water, it'll always separate into hydrogen ions and iodine ions. There's no going back. Okay, and that's the property of being a strong acid. Strong acids do not have reverse reactions. Okay, in general, I think you can reverse these reactions, but it would take very extreme amounts of very extreme conditions of manipulating Le Chatelier's principle. Okay, this column here we will discuss later. This is the Ka, and if you remember what K stands for, that's an equilibrium constant. So at some point in this unit, we will be talking about acid-base equilibrium calculations. But these ones, the Ka value of strong acids is very, very large. So the interpretation of that is that it heavily favors the products. Heavily favors products. All right, and that's basically what some of the things about this table and strong acids, what they mean. All right, now the rest of the table is basically weak acids, and we'll discuss that in a moment. Now, strong bases are at the very bottom of the table, and it's kind of awkward, this table particularly, because it shows only two types of strong bases, so the oxygen ion and NH2, but in reality, most common strong bases are actually some form of metal hydroxide. The most common one being sodium hydroxide. That's the one we use most often in the lab because it's relatively cheap and not super dangerous. Potassium hydroxide is another relatively common strong base found in drain cleaners. Calcium hydroxide is another one we use quite often. This one's actually rather confusing because if you look at your solubility table, this is really interesting. Calcium hydroxide is actually considered a low soluble compound, but it is still considered a strong base because it is a metal hydroxide and creates lots of hydroxide ions. Okay, so part of the reason, again, many strong bases are metal hydroxides is because they will create hydroxide ions in solution. Okay, so if you remember from our definition of Bronsted-Lowry bases where they accept hydrogens, most common strong bases are actually metal hydroxides, and rather than accepting hydrogen ions, they actually just create hydroxides. Now, the really neat thing about that is it doesn't actually invalidate our Bronsted-Lowry definition of strong acid, strong base, because if you were to write out the equation for a metal hydroxide dissolving, so let's take sodium hydroxide. This will dissolve into sodium ions and hydroxide ions. The hydroxide ions will then do the following to water. And it seems kind of silly to be writing this, but this is what happens. The hydroxide ions will actually attract one of the hydrogens from water, and there's the base portion of it because it is taking or receiving a hydrogen ion to create, and oddly enough, it doesn't actually change the reaction at all because it just forces the water to become hydroxide. This is kind of like the missing step that nobody really talks about because, like I said, it doesn't actually change anything. You still end up with hydroxides in water. But anyways, but that's why, I guess this is why this is considered you can consider this a base using the Bronsted-Lowry definition, because it does create hydroxides, and those hydroxides will end up taking hydrogens from the water to create the same thing. But anyways, so this definition of strong base or metal hydroxides being strong base doesn't invalidate the Bronsted-Lowry definition. In a roundabout way, it still accepts hydrogen ions. Okay. It's easier to show that the metal hydroxides are Arrhenius bases, because the Arrhenius definition was to create hydroxide ions. It's a little harder to see that this is a Bronsted-Lowry base, because it's like, well, it creates hydroxide ions. I don't see any reason for it to accept hydrogens, but it actually does, because in the presence of water, the hydroxide ion will strip hydrogens from the water to create water and hydroxide ions. Kind of weird roundabout, kind of circular logic, but it is kind of how it works. So those are strong bases, and most often we'll stick with metal hydroxides as strong bases, but the oxide ion and the NH2- ion are also strong bases. All right, now everything else on the table is considered a weak acid or a weak base. So as you can see, if I go back to, here we go. As you can see, there are quite a lot of strong acids, or sorry, not strong acids, weak acids and weak bases, and they all have an equilibrium arrow, meaning that when they are in solution, they end up creating an equilibrium of forward and reverse. So they create an equilibrium of things turning into bases and the bases turning back into acids. Okay. Now, with this in mind, it's very important that when we are dealing with weak acid, weak base equilibrium, depending on what we're analyzing, it is important that we write the correct equation. Okay. And what I mean by this is, because we have a forward and reverse reaction, and this is very important, especially for substances that can act as both an acid and a base, like for example, this one here, HSO3-. This substance here is an amphiprotic substance and has the ability, to become an acid or a base depending on the situation. So it's very, very important to write down the correct reaction for the correct situation. So here's an example: H2S and HS-. So H2S is the weak acid. So this is a weak acid, and this is the conjugate base of H2S. Okay. So when H2S is acting as an acid, we can write the forward reaction of that particular equilibrium. So as you can see in this one, the H2S is acting as an acid. It gives the water a hydrogen. It then becomes HS- and becomes this, H3O+. Okay. Now, HS is interesting because it has the ability to act as an acid, because it can give away this hydrogen to become an acid. And in reality, if you wanted to deal with another acid reaction, we could use that. Now, if we say that HS- is acting as a base, we would have to write the reverse reaction for this. Okay, so if we say HS- is a base, we would write the reverse reaction, because the reverse reaction shows the HS- acting as a base, in that the hydrogen from the water, one of the hydrogens goes here and gives us H2S. Okay, so we have to be very careful when dealing with some of these substances, because if I were to say HS as an acid, so HS- as an acid would actually go the other way. So we would go HS- plus H2O, and as an acid, the HS- would give up its hydrogen ion to the water to create H3O+. Okay, so when we look at the weak acid, weak base table and the problems we're dealing with, we have to be certain that we are using the correct reaction. Okay. And this will become very important when we start dealing with acid-base equilibrium calculations. And we'll revisit this topic of, do we write the forward reaction or do we write the reverse reaction? What do we do with the K values? Okay. That's a topic for another video though. All right, so sort of quick recap of what we've talked about so far in this video and other videos is that when a substance acts as an acid, because of the way that acids work and the way the hydrogen ion works, you'll always end up with H3O plus being produced. So if I have a generic equation, you could write like this: acid, when combined with water, will create H3O plus and a base. We'll say conjugate base. Conjugate base. Okay. And the reverse, if a substance is acting as a base, it'll always create hydroxide ions. So if I were to write down base plus water, this will create OH minus and its conjugate acid. Conjugate acid. Right, so just remember this sequence, okay? And we always have to add in this plus H2O. I think the table doesn't have that. Yeah, the table doesn't show that, but let's have a reminder for yourself is that if I'm acting as an acid, I add it to water to create hydronium. If I'm acting as a base, I add it to water to create hydroxide. And then the other substance is a conjugate base or a conjugate acid, depending. All right, so here's an example. For methanoic acid, we're going to write the forward and reverse reactions for this. So methanoic acid in its acid form. Methanoic acid, if you look on your table, has, I think, down here, there's methanoic acid. Okay, there's HCOOH, it's an organic acid. So in the acid equation, HCCOH, we will add this to water. This will create hydronium, H3O plus, and in the conjugate base it creates will be HCOO minus. Okay, remembering that for an organic acid, this is the H that gets given to the water. Now the base version of this, if I were to take the HCOO minus, add that to water, so this would create hydroxide ions and then the HCOOH, because this water will give up its hydrogen to here. It'll be, the water becomes OH minus, and then you recreate the acid. Okay, here we go. So all the weak bases, all the weak acids have this this type of relationship with its conjugate base, where you have the forward reaction is the acid reaction, and the reverse reaction is kind of the base reaction. Okay. All right. Now there's a couple other relationships from this table that I'd like to highlight. Generally speaking, if your substance is higher on the left side of the table, that means it's a stronger acid. And if your conjugate base is on the right side and it's lower, that means it's a stronger base. And then if you have a stronger acid, its conjugate base is weaker. And similarly, if you have a stronger base, its conjugate acid is weaker also. So if I were to go to, say, back to my table, this substance here, iodic acid, because it's very high up on the left side, iodic acid is actually a pretty strong, weak acid. And then if I look down here, say like for example here, PO4 3-, so that's the phosphate ion. The phosphate ion is actually a pretty strong, weak base. Okay, and then these ones in between kind of are all kind of like all over the place. So like for example, like boric acid down here, pretty weak acid, but its conjugate base, H2BO3-, this is actually a pretty strong, weak base. Boric acid, weak, very weak acid, while its conjugate base is not as weak of a base as others. Okay, so strength of acid goes up as the acid is on the left side. Strength of base goes down as the base gets closer to the bottom right here. All right. Now there's one other effect we need to talk about, and that's called the leveling effect. The leveling effect is really interesting because it's what happens with strong acids when they dissolve in water, and the same thing is for strong bases. Now, strong acids, because they fully dissolve in water, the hydrogen ions will create an equivalent amount of hydronium, and similar can be said for strong bases. A strong base, when it dissolves in water, will create a similar amount of hydroxide ions. Okay. And I'll illustrate this with hydrochloric acid. So hydrochloric acid, this is the overall reaction for hydrochloric acid. It's not quite correct. What I should have written down actually is the following. So hydrochloric acid, HCl, will dissolve to create H plus and Cl minus. And because it's strong, this will happen 100%. So if I had, say, like 1 molar hydrochloric acid, this would create 1 molar H plus and 1 molar Cl minus. Now the H pluses, the 1 molar H plus, will combine with an equivalent amount of H2O to create this H3O plus. So if I have 1 molar H plus, it will combine with enough water to create an equivalent amount of H3O plus. And every strong acid will do this. So if I have 1 molar hydrochloric acid or hydrogen chloride, it'll create 1 molar or an equivalent amount of hydrogen ions, and those hydrogen ions will combine with enough water to create an equivalent amount of hydronium. And that's the leveling effect. Okay, it seems kind of moot because it's like, well, that makes sense because we have 1 molar hydrochloric acid. It would make sense to create 1 molar hydronium. Okay, and that's true for all strong acids. Weak acids don't do that though, because a weak acid doesn't fully dissociate into hydrogen ions. So if I had a weak acid, like let's say hydrogen fluoride, if I had 1 molar hydrogen fluoride, because this exists in equilibrium with its ion, like this is not 1 molar hydrogen ions, okay? Because some of those hydrogen ions will recombine with the fluoride ions to recreate the 1 molar HF. So a weak acid does not do this, okay? So weak acids do not create an equivalent amount of hydrogen ions. So the amount of hydrogen ions, the amount of H plus ions depends on Ka. The higher the Ka, the more hydrogen ions. The lower the Ka, the less hydrogen ions. Okay, because again, if you recall back to our equilibrium unit, K determines how heavily favored the forward or reverse reaction is. If K is really large, it heavily favors the forward reaction. If K is really small, it heavily favors the reverse reaction. Okay, so for a weak acid, the amount of hydrogen ions that gets created, and by extension the amount of hydronium that gets created, depends on this value here. Whereas for a strong acid, the amount of hydronium that gets created is equivalent to the amount of actual acid that is present. Okay. Now the same can be said for a strong base. A strong base does the exact same thing, only with rather than creating hydronium, it creates hydroxides. Okay. All right, and then to sort of reiterate that, the complete dissociation of hydrogen chloride means that for every amount of hydrogen chloride, or every mole of hydrogen chloride, an equivalent number of moles of H3O plus is produced. And this is true for all strong acids. Okay. But then keep in mind that for H2SO4, this only dissociates into one hydrogen and then HSO4 minus. Okay, so even for H2SO4. Okay, so H2SO4 does not actually generate twice as much hydrogen ions. It only generates an equivalent amount of hydrogen ions. Really interesting. And that's because HSO4 is a weak acid and doesn't actually fully dissolve. Okay. Now we call this the leveling effect because the overall effect is that strong acids and strong bases all have the same strength. Basically, they fully dissolve. That's what the leveling effect means. So basically, both strong and weak, not strong, both strong acids and bases. That's what I meant to say. So both strong acids and bases fully dissolve, and that's why it creates equivalent amounts. So this is what the leveling effect is. Basically, it allows us to say that 1 molar hydrogen chloride will create 1 molar hydronium, and similarly, if you take something like sodium hydroxide, this will create 1 molar of hydroxide ions. Okay, equivalent, but only for strong acids and bases. Weak acids and bases don't do this. Okay, and we'll talk about what happens with weak acids and bases in a future video. All right. Now, if you have your textbooks with you, the assignment questions that you should go over are as follows. I'll give you a little bit more review as to what we just talked about. And if you guys have any questions, you know how to get a hold of me.